Okay. Organic chemistry. Is the covalent chemistry of carbon. Do we all know what covalent means? If you had to write the definition of covalency in less than 10 words, what would that definition be? That's only 2 words. Sharing electrons is 2 words, and it gets to the crux of what we're looking at. But a covalent bond is 2 electrons shared between 2 atoms. So this is not the ionic type of bonding that we saw between metals and non-metals, where the metals undergo oxidation, they lose electrons, because electrons are negative, it leaves a metallic ion that has a positive charge, and then they interact with the non-metal, gains electrons by reduction, becomes an anion, and the cation, which is positive, and the anion, which is negative, have an electrostatic attraction to one another. That's ionic. We won't be doing any of that. Covalent, 2 electrons shared between 2 atoms. Now, how many types of bonding are there? General chemistry, how many types of bonding did you learn in, maybe not learn, but hear about in general chemistry?
3.
Okay, what would they be?
Single, double, and triple.
Oh, okay. So single, double, and triple, they're all flavors of covalent bonding. Those are types of covalent bond. I'm talking about just the big picture. So we have ionic bonding and covalent bonding. That's 2 types right there. What else is available to me?
Hydrogen.
Hydrogen bonding, that would be 3. What's the 4th one that's in the book? It's the one that nobody talks about. It's in the book. Metallic. That's the bond between metals that keeps them all together in a pure element. So this is covalent, and it means shared between 2 atoms. Our simplest case on the day that we did molecules, because atoms combine covalently to make molecules. Ions combine ionically to make compounds. Distinction. Our organic molecules, all of our stuff, is going to be molecular. We don't use the word compound. Compound is for ionic. What was the simplest, the day that you learned what a single bond is? What was the simplest molecule? It's a combination of the 2 simplest atoms.
Is it CH4?
Okay, well, that's going to be our simplest molecule of carbon, but even simpler than that, yeah. So we're going to take a hydrogen and a hydrogen. The day that we learned about Lewis structures, we said, here's a hydrogen. The hydrogen's in group 1, therefore has 1 valence electron. And this hydrogen is in group 1, and therefore has 1 valence electron. And if you can have this atom and that atom combine, ooh, that's a covalent bond. Let's make 2 electrons. between two atoms. This is now a molecule. That was as simple as we could get. And that was a 1s orbital holding onto this electron, and that was a 1s orbital. And so a 1s and a 1s, so here's my neutron, there's my nucleus. The nucleus of a hydrogen atom only contains a proton. And then there's my other nucleus, and then I have a cloud of electrons in a 1s shell. And I have another cloud of electrons in this 1s shell. If they overlap, I make a sigma bond. Remember sigma orbitals? It's a lowercase sigma. What does a sigma represent? This is now what we call a molecular orbital. It's going to hold two electrons. All molecular orbitals just hold two. The sigma part tells me that there's direct overlap of those atomic orbitals. I took this one, I took that one, and I had them directly overlap. And now it's skinnier here, and most of the density is between the nuclei of this new molecule. Now, we go, so that's as simple as it can get. When we get to do carbon, carbon has p orbitals. There's an x, and there's a y, and there's a z axis. And carbon is in the second period, so that is the 2py, and the 2px, and the 2pz. If we're going to make covalent molecules with carbon, now I have to do a direct overlap between the P, which is that dumbbell shape, and the S, which is a spherical shape. There you go. That is direct overlap. That gives me a sigma bond, and we equate sigma bonds with single bonds. And we've already established a little bit earlier than we needed to that molecules are some molecules are capable of having single bonds or double bonds or even triple bonds. Double bond contains a sigma overlap, direct overlap between the atomic orbitals, and then something else. What was the something else? It's a pi bond. It's when the p orbitals line up but don't overlap. Just symmetry allows the electrons to migrate to a molecular orbital that sits between the nuclei. Okay? And there's plenty of time for us to do that. That's going to be in chapter. I put this away. That's going to be when we do alkenes, a couple of weeks from now. So we'll be week 4. 4 weeks before we even need to talk about that kind of bond. We all right with this? Okay. If I'm a hydrogen atom, I'm in group 1. How many bonds can I make?
1.
1. Okay, so hydrogen's different. All the other stuff, let's see if we can spot it. There's a periodic table right there. Let's see if we can spot the trend. We're going to read down the group from top to bottom. Group 1, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. Did you spot the trend? Hydrogen's not like the others. What do the others all have in common?
They're metals.
How do we know? Something that ends in ium means it's a positive ion or is capable of making a positive ion. Think about the metals. Lithium, sodium, potassium, magnesium, calcium, strontium, rubidium, scandium, titanium, vanadium, chromium, moving across the periodic table right there. They're all ending in ium. Hydrogen doesn't end in ium, but you can make a hydronium ion, remember that? So it can go positive. So hydrogen's capable of being ionic. When it's capable of being covalent, it can only make one bond. Do we need anything?
No, I was just coming in to say hello and write my phone number down in case they need something.
One electron in a hydrogen, knowing that a covalent bond is two electrons shared between two atoms, it's only capable of making one bond. So the next leap of thought should be, well, let's move to group 2. But group 2 is full of metals. Metals are capable of two types of bonding. What would they be? Metallic bonding, because they're metals. Metallic bonding is named after them. And ionic, where they lose electrons, they become cations, and then they combine with non-metals. It's only the non-metals that do covalent bonding. Covalent bonding is between non-metals. So if I want to prove a point, I just showed you hydrogen on the board. Hey, here's our simplest molecule. Hydrogen's an anomaly. It's in group 1. It's in with the metals. Is hydrogen a metal? Yeah. Yeah, it is. At really close to absolute zero, it starts to exhibit metallic behavior. It is where it belongs, but it's a gas, and it's very, very small, and therefore is off doing its own thing, and is capable of showing ionic and covalent behavior. But it's happy to mix in with the non-metals and do this covalent stuff as well. So it's an anomaly. We're okay with that. So I can't do anything in group 2, and then the transition metals, it says metal in the name, so they're all off limits as well. If I want to look at covalent stuff, I have to be really a non-metal. So I look at group 3, and group 3 it's got aluminum in it. Ooh, I erased that. Anybody foreign? Is anybody from Canada or Europe? One of those words is spelled wrong. The Americans say aluminum, and the British say spelling. It's a metal. Somewhere around the Mayflower that I dropped. Okay. So if you spell it the correct way on any of our tests, I will dock you points because this is America and we have to abide by the rules. However petty and unpleasant they are. So we've got to be non-metal. Now boron at the top of group 3 is a non-metal, and then carbon, nitrogen, oxygen, fluorine, neon. They're all non-metals. So the periodic table is mostly metal. How can you tell? I mean, what's the definition for another metal? I gave you something and said, tell me if that's a metal. How'd you know?
Oh, it's not shiny or,
Ooh, shiny. Or
I don't know, like metals that were
some metals are hard, some of them are very, very soft. Sodium is like cork. You can pick it up and rip it. But you wouldn't want to rip it with your bare hands because the moisture on your hands would evolve hydrogen. And that would be dumb. But you can cut it with a knife, butter knife. Okay, how about that? For those of you watching at home, I'm off screen. The first item was a piece of cardboard, and the second was a battery. How can you tell that's a metal?
well, then the appearance, because it's shiny.
It's shiny, and
Like I know it can talk,
how do you know?
because
It's
it's
a battery. So metals conduct electricity. How does it feel?
hard,
Okay, and cold
cold.
because it conducts heat, conducts the heat away from your hands. So metals are conductors of heat. They're conductors of electricity. They are malleable and ductile. Malleable means mallet and malleable both have the same prefix. Can be hammered into shape. You can hammer metals into shape. And when you do, they make a characteristic ding sound. They make a ringing sound when you hit them. That's a physical manifestation that what you're looking at is a metal. And they're ductile, which means you can extrude them into wires. And if the object that you are given, we can hammer this battery and change its shape. We can do that, and we can make it conduct electricity, and we can feel that it's cold. This one, we cannot extrude that into a wire, and it doesn't feel cold to the touch, and it doesn't conduct electricity. And we very creatively call things that are not metals non-metals. And when you look on the periodic table, it's just the extreme right-hand side. It's the top right. It's only this little bit, only this bit over here. And our covalent bonding is between non-metals. So I've got this zigzag right here. All of those are metals. So the only things that I have to concern myself with are up here. And it turns out carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, that's biochemistry right there. That's all of biochemistry. You really won't need anything outside of that list. We're going to throw in some chlorine and bromine and maybe some fluorine as well, and that's it. Okay. All the covalent chemistry here. So, the question gets to be, if I'm on the left-hand side of the periodic table, I'm a metal. I'm going to be ionic. If I'm on the right-hand side of the periodic table, then I'm going to be a non-metal. Well, I'm going to have that thing that we talked about quite a lot in general chemistry. That thing, that characteristic, that as you move further to the right and further to the top, becomes more and more and more pronounced, that non-metals do, that metals don't do. It's called electronegativity. What was electronegativity? Definition. Electronegativity. Anybody? The ability to pull electrons towards you in a covalent bond. And that increases diagonally right here, which means fluorine is our most electronegative atom. Nitrogen and oxygen and chlorine are also highly electronegative. Okay, so if I'm on the left-hand side, I'm a metal, going to be ionic. If I'm on the right-hand side, I'm going to be a non-metal, which means covalent chemistry. And the more to the right I am, the more greedy I'm going to be with the electrons inside this covalent molecule, which then gives us polarity. Remember polarity? It's going to give us polar bonds, and therefore perhaps polar molecules. And polar molecules open up a completely new world, because the physical world is literally divided between non-polar molecules and polar molecules. There is a barrier. There's a literal barrier. This is oil and water. They don't mix. And some of our molecules are going to be non-polar, and some of them are going to be polar. And that's going to explain a whole lot of behavior. So in order to do that, I've got to just figure out what side of the periodic table carbon is on. There it is. What side of the periodic table is carbon on? On the right. Okay. That was it. I was thinking of making that like a take-home question. On the right. I'm glad we got that out. I mean, it's kind of important. It kind of is important. It's on the right. We can all agree with that, right? Carbon is on the right-hand side of the periodic table. You know, it's just that, how many groups are there on the periodic table? You shouldn't have to look at the periodic table. We should not have to look at the periodic table to know how many groups are on the periodic table. There are 8 groups on the periodic table. And when somebody asks you a really dumb question like, hey, is carbon on the left-hand side or the right-hand side of the periodic table? As I see it, there are 4 possible answers. It's on the right. It's on the left. It's in the middle. Or I seriously don't know. There are 8 groups on the periodic table, and carbon's in group 4, which makes it in the middle. Carbon's in the middle, because there are 8 groups, and carbon's number 4, so carbon's in the middle. Okay, and we can move on. Carbon's in the middle of the periodic table. We can move on. But just just want to get that out there. That if there are 8 groups on the periodic table, and that's number 1 and that's number 2, and that's number 3 and that's number 4, and then 5 and 6 and 7 and 8, then halfway it's actually there. The group 5, 6, 7, and 8 are on the right-hand side of the periodic table. And groups 1, 2, 3, and 4 are on the left. So what side of the periodic table is carbon on? No, it's on the left. Carbon is on the left-hand side of the periodic table. Still a non-metal, just gets in under the wire. Non-metal, left-hand side of the periodic table. Everything on the right-hand side of the periodic table pulls electrons towards itself in a behavior that we have called electronegativity. Pulls electrons this way. If you're an electron, you get pulled towards the chlorines and the fluorines and the oxygens of the world. They're electronegative. They pull the electrons towards themselves. If you're on the other side, then you push electrons that way. And you're electropositive. So these pull electrons, and then these push electrons. And this is going to explain something really fundamental that comes in like chapter 2 or chapter 3, that everybody who has ever taken organic chemistry will tell you that they know right off the bat. Oh yeah, the carbon goes positive, and you can change the number of carbons that are around a central carbon that has a positive charge, and they're going to it changes from being a primary to a secondary to a tertiary carbocation, and tertiaries are the most stable. And then you ask them, why? And they crumble because they have memorized the textbook, and they have memorized a trend, and they think that knowing the words in the trend means that they understand it. But they have not understood anything, because they think the carbon, because it's a non-metal, is on the right-hand side of the periodic table. Carbon pushes its electrons. All of the other non-metals that it interacts with are going to pull electrons. It's going to be a fundamental difference in its behavior. And this is going to just, it'll be important. Okay. Things we thought we had learned in general chemistry and would never have to do again. Electron configuration. Nice and loud. Tell me what the electron configuration for carbon is. There you go. 1 is 2.
I don't remember what the second letter was.
Read from the periodic table.
2S2.
You just put your finger on, you can't literally put your finger on the periodic table, but you can pretend, and you just read them across. So period 1, that's the big 1. That's my principal quantum number. That's the number of my period. S, because we're in the S block. That's the S, this is the P, that's the D, this is the F. We're in the S block. I put 2 electrons into that 1s orbital. And then when it's filled, I come around and I start a new line. And I do the second period's S orbital, which is 2s2. And then to get to carbon, which is in group 4, 2p2. So how many core electrons does carbon have? Remember what core electrons are? They're inside the outer shell being called the valency. Let's back up. How many valence electrons does carbon have?
4.
4. It's in group 4. Therefore, it has 4 valence electrons. It's those 4. In the 2 shell, these are core electrons. They're not available for chemistry. The chemistry of any atom is performed only by the valence electrons. Atoms, here you go, there's an atom, it's got some protons and neutrons in it. Positive charge right there. And then a great big cloud of electrons. Well, the electrons are negative. So when atoms come close to each other, they repel. They have to come together with some kind of purpose. It's going to be to our ultimate benefit energetically if I share electrons with you. But the outside shell right here, they're going to repel. So the chemistry is done on the very, very outside of the atom. It's not done anywhere here in the middle. Only done on the outside. Okay. So carbon has 4 valence electrons. And when you learned Lewis structures in general chemistry, we learned if you have 4 valence electrons, then you can just go, oh, shared two electrons right here, and share another, and then share another. So, oh, before you know it, I've got 8 electrons. I meet the 8 electron rule. That means I have 4 bonds. So carbon always has 4 bonds. That was one of the cardinal rules of Lewis structures. Carbon always makes 4 bonds. Nitrogen always makes 3. Oxygen always makes 2. Hydrogen always makes 1. Chlorine always makes 1. Fluorine always makes 1. Do you remember that? So how many would sulfur make? 2. Always, without exception. It's in group 6. 6 plus 2 is 8. It's just the 8 electron rule. What about phosphorus? 3. It's underneath nitrogen. They're in the same group. It means they have the same chemical behavior. Okay, so we're all good with this. And then we care to look. And it all goes horribly wrong. Because what follows electron configuration just by 1s2, 2s2, 2p2 is that thing where we put the electrons in the boxes. And that was, there are 3 rules that determine what my electron behavior is. What were those 3 rules called? First one's called Aufbau. Aufbau means that's the building up process. It means you start at the bottom. It means I cannot, if I'm going to build a carbon atom from scratch, can't just start putting electrons into the P. I have to start closest to the nucleus. So my first electron, remember electrons are arrows with a single barbed arrowhead. My first electron goes there. Carbon has atomic number 6. So there's going to be 6 electrons because atomic number is the number of protons. The number of protons has an equal number of electrons. Aufbau says I have to put my electrons at the bottom to start with. And then there is Pauli's exclusion principle, which says if you're going to put 2 electrons in the same orbit, say what? They have to be spin opposed. So there you go. I've described 1s2. Here's my 2s1. 2s2. So Aufbau and Pauli's exclusion principle have got a Third rule. Aufbau, Pauli's exclusion principle, and then when did you all take general chemistry? Feel like a long time. Hund's rule. And Hund's rule says, in a degenerate set of orbitals, like this, where the 2px, the 2py, and the 2pz are all of the same energy, put them into empty orbitals before you pair them up. That's Hund's rule. So 2p1, 2p2. Okay? Now, cast your mind back, way, way, way back, all the way back to the very, very beginning of general chemistry, where you're told, here's a molecule. It's got two types of electrons. These are paired electrons. What do we call paired electrons? Non-bonding pairs of electrons. These are non-bonding. Non-bonding. The unpaired electrons are bonding electrons. So how many bonds can carbon make? Look at the diagram and tell me. It's only got two unpaired electrons. How many bonds can it make? Two. The electron theory for carbon says it is only capable of making two bonds. It has two unpaired, therefore bonding electrons, which means it can only make two bonds. But we know from observable fact that carbon doesn't make two bonds. It makes four all the time, every time. So the theory as described in your general chemistry book is wrong. Linus Pauling won the Nobel Prize twice, did this. What if we just stole that electron and moved it to here? How many bonds could it make now? 4 unpaired electrons. And this is the behavior that carbon exhibits. That rather than have those two electrons paired, it hybridizes itself. This is called a valence hybrid. Linus Pauling invented a type of bonding theory called valence bond theory. He won the Nobel Prize for it. It has since been, I'm not going to say discredited, but we've moved on because molecular orbital theory is a better description, but the math is at a higher level. So this will do. Carbon is capable of making 4 bonds because it has 4 unpaired electrons in its valence hybrid. We're going to give this a name. This hybrid right here consists of an S and a P and a P and a P. And we call that an sp3 hybrid. sp3 is now synonymous for the rest of your education with 4 single bonds to a central carbon. That's going to be the majority of what we look at. It's also called tetrahedral. Its geometry is tetrahedral. We're just going to call it sp3. Okay? I'm gonna do a few updates on Blackboard. Your syllabus is garbage. I'm gonna completely rewrite that, and yeah, I thought I fell into my lap. I'll just duplicate that one. Didn't quite work. And I'll see you on Wednesday. I'll post some little expectations. Lab for this week is basically just safety check-in. Nothing going on.
What?
Thank you.
That's an option.
Oh.